Good morning. Today is December the 7th, year 2011. I'm staying in a hotel in Yokohama, Japan. But anyway, let's start.
Okay, the next talk is an optimization of randomized approximability and Boolean constraint satisfaction problems. And the speaker is Tomoyuki Yamakami.
Well, thank you very much. Well, this talk is about an optimization problem. Particularly, the optimization problem is based on Boolean constraint satisfaction problems. As I said, the basis is the constraint satisfaction problem, or simply we call it CSPs. And we use this optimization version of CSPs. The particular is we are interested in multiplicative objective values. And what is new? And we are going to prove the so-called classification theorem that's actually characterized in all possible maximization CSPs. And why this result is new? Earlier, Craigdall and Connor, Sudan, and Traveson, and Williamson, they actually talk about the approximation complexity of the optimization CSPs. But in that case, they actually use this additive measure. So we are going to explain what those concepts are. So that our result actually complements their results. Now, so I start with the very brief introduction to the constraint satisfaction problem here. So that our example here is a satisfiability problem, and I just picked up one logical formula as an input in CNN form. And here, this is just one example. So this is an ands or ors, three ors. For simplicity, I just ignore the negation operation here. We can just write it down, this particular formula in the form of the functional version here. So this is just the product of the three ors. And we can possibly ask many different questions. For example, if they need satisfying truth assignment, and that satisfies this particular formula, so this is a decision version of the CSP. And if you just simply ask how many of those truth assignments, that's the counting CSP. And the third one here, so this is our main theme here, is we actually try to search the optimal truth assignment. So that is an optimization CSPs. We are actually interested in the constraint. Constraint is a function, just a function mapping from the k-bit strings to the non-negative real numbers. And to describe this constraint, we just used a very simple kind of a simple way to describe it. Using the row vector of in this particular case, it's 4 elements. And if you have the three ternary constraint case, we have the row vector of 8 elements. The concise example here is the order is actually represented by the row vector of 0, 1, 1, 1. And the logical implication is 1, 1, 0, 1. And the other parts are singularly defined. So now, generally speaking, the CSP has taken two different types of items, inputs. The first one is the variables, and we have a bunch of constraints that are defined over the variables. And CSP could be found in many different areas, including artificial intelligence and database theory and scheduling, graph theory, and even in statistical physics. So considering the CSP is very useful and very practical in some sense. But here there's one nagging question. So can we efficiently solve all CSPs? Before defining optimization CSPs, so I just want to briefly explain the decision version of CSPs. This is much easier to understand. So decision version of the Boolean CSPs are all NP problems. So this is just a subset of NP problems. And usually we just restrict our interest within constraint language. Constraint language is just a set of constraints. So this is the constraint that we can use as an input. So that more formally, in the decision version of CSP, we just need to write it down to the CSP of f. So f is a set of constraints. And instance to this problem is the Boolean variables and a set of constraints. But here, the constraint is chosen from f. And our question is to determine whether there exists a truth assignment that satisfies all constraints, the given constraint here. So the concrete examples here include the satisfied with the problem and the colorability and vertex coloring. And what is nice about it, considering the constraint satisfaction problem, because, for example, in the decision version of the CSPs, if you take a look at it in the whole world, the world with the NP problems, assuming that the P is different from NP, earlier, Lautner proved that all NP problems can be classified into infinitely many levels, different levels. Between the polynomial time computable problems and NP complete problems. But here, if you look at the CSP problems, so we only have two levels, two categories. The first one is the polynomial time solvable or computable CSPs. The rest belong to NP complete. So nothing between. Now we move on to the optimization CSPs, and that is the main theme of this talk. As you know, an optimization problem, or particularly the combinatorial optimization problem, can be defined by the three items: the set of input instances, and the feasible solutions, and the objective function or measure function that assign the value to each individual feasible solution. Now, we call the solution optimal. Usually it's an optimization consider either maximization problem or the minimization problem. So we are sticking to the maximization problem in this part. So the solution is called an optimal whenever the y solution gives the maximum optimal objective value. So we have similar to the complexity class P and NP, we have PO and NPO. The PO is the set of class of the polynomial times solvable optimization problem, and NPO is the class of the NP optimization problems. Now we are actually here is I'll give you a very quick example of maximization problem, the so-called maximum cut. The maximum cut, so the given instance, so this is the undirected graph, and we are trying to find the partition of those vertices into two disjoint sets, V1 and V2. For example, here, so the V1 contains the three elements, three vertices, and the V2 contains the three vertices. And now the task is to choose the partition so that the maximum weight of the cut can be achieved. So in this particular, here the weight of the cut is the number of the edges that's actually crossing between the two sets. So in this particular case, we have the 4 edges that's actually crossing the border between the V1 and the V2, so that the weight of the cut is exactly 4. And it turned out to be the max optimum. So formally, we'll define the maximization problem in the following way. The maximization CSP takes the instance of the variables and the constraints, and the constraints have to be taken from this fixed set F. And we try to find the truth assignment that maximize the summation of all objective values. And we will use the abbreviated term, the max CSP of F. One example of such max CSP is the max cut, as we see. And in comparison, we call such measure additive measure because then we actually use the summation here. The Craigno, the Constraint, the Traveson, and the Williamson, they actually showed them a very nice dichotomy theory, so that that says all max CSP can be classified into only two categories, as before. Polynomial solvable max CSPs, or it's an APX complete max CSPs. So next our challenge is to explore other types of optimization problems. And if you look at the past literature, there are a number of papers that actually talk about the products of objective values instead of the summation of objective values. For example, in linear multiplicative programming, this is the problem to minimize the product of the two positive linear cost functions subject to the linear constraints. In the field of the geometric programming, they actually have some argument as how to reduce the product objective function into additive one. And the third example is more relevant to my talk. So this is a variation of the max knapsack problem. And the maximization here is measured by the product of the objective values instead of the summation of the objective values. And those product objective functions can be, well, I just simply call them the multiplicative measure in comparison to the additive measure. So our task is, this is the one example here, one very quick example. It's max for IX, so the maximum product independent set. So it's a given instance, this is the undirected graph. And each vertex, well, we assigned a number, non-negative value, real number, to each vertex. And we try to find its independent set. Independent set means that is the subset of V, the total vertex set, and such that each edge is incident on at most one vertex. So that means here those three vertices going to form an independent set. And our task is to maximize the product weight. In this particular case, we have three numbers, 3, 5, 3, 4, 5, so the multiplication of those numbers becomes 60. And another one is the variation of the max prod IX. Instead of them taking any graph, then we just restrict our interest within the bipartite graph. In this case, those are the independent set, and the product weight is 60. So formally, we'll introduce the max prod CSPs. And this is pretty much similar to the max CSP. The only difference is instead of taking the summation here, we will use the product. So this is the multiplicative measure. Now, we try to classify all possible max prod CSP into several categories. We'll use the randomization approximation scheme. So the randomized approximation scheme, or the RAS, takes the pairs and it's a standard int x and error tolerance parameter epsilon. And this algorithm has an output y with high probability, and so that the y gets very close to the maximum optimal value. And here is an error is relativized, so that the ratio between the two values are between 2 to the minus epsilon and 2 to the epsilon. And when this algorithm runs in the polynomial time, so we call it the Fourier polynomial time randomized approximation scheme. The important thing is that even though an alpha beta is approximated in this sense, but that does not guarantee that an alpha plus beta is approximated in the same way, same meaning. So now, we're going to do the reduction here. So the two optimization problem, P and Q, and the P is reducible to Q by a reduction machine N. That means that M is an probabilistic Turing machine working on the input X and epsilon. And using oracle represents any graph that solves Q. And using this oracle, the M solves P within the polynomial time. So that's the meaning of the reduction. So this is actually pretty similar to the standard polynomial time reduction, many one reduction, Turing reduction, and we will use those notation. Now, we'll state the result. So before describing the main theorem, we're going to do the abbreviation here. So U stands for the set of all unary constraints, and ED stands for the set of constraints, and each of which is expressed by as a product of a unary constraint and equality function, and XOR function. And AF is the set of Arkin-like constraints. The definition is slightly more complex, so please take a look at the proceedings. And IM opt is the set of constraints, which is represented by the product of the unary constraints and constraint of this particular one. 1, 1, lambda 1. The lambda is located between 0 and 1. And a particular example here is 1, 1, 0, 1. This is actually logical implication. This belongs to the IM opt. So in a sense, that is an extension of the implies function. So now we have one big assumption here. We allow any unary constraint as a part of the input for free of charge. So this seems to be a little weird, but a lot of people actually use this assumption, because this assumption makes the statement or the result clean and simple. So now we'll prove the so-called trichotomy theory. Well, instead of the two categories, we actually have 3 different categories here. F is a given set of constraints F. So the first is F is a subset of either AF or ED. Then the problem, max problem CSP, is solvable in the polynomial time. Otherwise, if F is a subset of IM opt, then this problem is located between the max prod BIS, the bipartite independent set, and the max prod form. And otherwise, then the max prod CSP, this problem is at least as hard as the max prod IS. 3 categories. And this problem can be solved, can be proven by the several claims and lemmas and proposition. And one of the proposition says that if F is one particular constraint that belongs to IM opt, then max prod CSP of F is as at least as hard as the max prod CSP of implies. But if F does not belong to an IM opt, then the problem is at least as hard as max prod CSP of G. G is either or not. So that whether F belongs to an IM opt or F does not belong to an IM opt, that actually makes a clear distinction between the complexity of the complexity of the max prod and the CSP. Well, thank you very much for attention, and that's all.
Questions? Yeah.
So could you go back one slide? So in your main theorem that you have the 3 categories.
Yeah,
but,
that's right.
I'm wondering whether the second category is really one category or not.
Yeah, that's right. You are right. So this problem, all the problems that satisfy this condition is located between this and this, but I'm not quite sure whether those 2 problems are actually coincident. So, but the so yeah, that's right. So you're right.
Maybe
I do not.
Yeah.
Yes.
Okay.
So my point of view is that either a problem is very simple or very hard or just the middle.
Thanks. Another question? No? Move on.
Thank you very much.